Hello, everybody. I'm Tony Fraser,
And I'm Kristen Lucy.
and we are partners for 622 and a couple of other classes. We've done a lot of projects together, and today we are going to be talking about something that I am pretty passionate about. We decided to work on this project because it's cool. It's kind of like one of those Mount Everest that our industry had to climb back in the 80s. And the problem is the post office problem. So a long time ago, the whole time that we had a post office before we had computers, there were always people that were in these mail rooms, and they would, look at the letter and then put it in a box, and that box would go to one place, and that box would go to another place, and basically they were, all just looking at zip codes and then putting them in boxes. And it was the world of automation, and we really wanted to sort of solve this problem, and the government wanted to solve this problem, and it was kind of a big deal. So there were some really smart people that took this on and they implemented this data set, and it's often used as kind of like the hello world for machine learning and neural networks, and it's called Mnist. So it's a big famous problem. We wanted to do it because we wanted to get familiar with it. We also had an assignment where we had to compare two models together, so this was perfect. So all right, so we'll kick it off. I'm going to share my screen. Okay, so this is what we're going to talk about. We used the MNIST data set, and we did k-nearest neighbors and neural networks, and we compared how good they were at predicting, um, you know, things in this data set. So what is the data set? Data set looks like this. It's a whole bunch of images, 70,000 of them. 60,000 are for training and 10,000 are for test. And it's basically just exactly what you see on the screen. They're just numbers. And this one right here, we don't exactly know if it's a 7 or a 9 or what, but the point of this data set is to digitize these numbers, then to predict. So here's what each one of these records looks like, these 70,000 records. You can see that I mean, it's not really stored in an image. There's no GIFs on this data set at all. It's 70,000 matrices of data. So there's positions, right? So there's this many across, 28 by 28 down. And then if you go down to that one and then that one right there, you see a 26. These numbers represent numbers between 0 and 255. So 0 is black, 255 is white, and then 180, it's a little bit closer to 255, so it's lighter. And then this one right here is a little bit closer to 0, so that's 38. So basically, on a 256 color palette, these are just, images. They look like this. That's how they're all stored. So yeah, so getting back to the purpose of this data set, we it's called the MNIST data set, and we used k-nearest neighbors and neural networks to compare the two of them. So at a high level, we have this summary. Obviously, one of these um, algorithms is much better than the other one. It's going to be neural networks, but we'll show you that in the conclusion. Some of these they behave very differently. One of them has to be trained a lot, and the other one just happens sort of quickly. Um, yeah, and then through our project, we talk about how we implement KNN. Kristen's going to talk about how we tune that a little bit. And then there's the neural network right there. And there's a little bit more information here. It's a little bit more of a complicated problem. And then we show training time and accuracy and scalability. And then we have this cool chart that talks about the individual digits. And then we wrapped up to conclusion. So yeah, so let me just sort of turn it over and we'll let Kristen take over for a few minutes.
It says you disabled screen sharing.
I will fix that. Apologies. There you go.
Okay, got it. Okay. So the first model we worked on was the KNN model. And the configuration included splitting the data into 80% training, 20% testing. And then we scaled the features using standard scalar to make sure that all the features contribute equally to the distance calculation. One thing about KNN is that it's a lazy learner, so it stores the entire data set and only makes predictions during inference. And then for the prediction process, the distance, the default distance calculation is the Euclidean distance formula. And then we selected the number of k nearest neighbors we wanted to use, and then we determined the classification method. So the key parameters for this were the number of neighbors, the distance metric, and then the weighting scheme. The default weighting scheme is uniform, where all neighbors contribute equally. And the performance metrics we got were the training time was 6.31 seconds and the accuracy was 94.7%. So it has shown to be a powerful approach. But the one downside to it is that it needs to be retrained over and over again. And neural networks, it is not like that. It's more adaptable to problems. So the next model we worked with was the neural network. And this is a little bit of the structure overview. Sorry if you can hear sirens in the background. I live in New York City, but so this is the layer analysis for the neural network architecture. It's kind of high level, but it kind of explains like what each layer does. And then the parameters used for the training configuration were epochs. I don't really know how to pronounce that. And the total number of iterations we chose was 10. And the batch size was 128 per gradient. And the validation split was 10% of the training data. And the optimization strategy used was ADAM, which is an adaptive learning rate optimization. And the loss function used was sparse categorical cross entropy, which is good for multi-class classification. And the performance metrics for the neural network were the training time was 11.37 seconds. So it took a little longer than the KNN model, but the accuracy used 97.4%, which is higher than the KNN model. So comparing the two models, obviously the accuracy was better for the neural network, but the training time took a little longer. So the reason why KNN has a faster training process is because it's a lazy learning algorithm. And the reason why the neural network takes a bit longer is because of the back propagation, weight updates, and regularization techniques. Yeah, so one thing to note between KNN and neural networks is that the scalability is different. Like when there's larger data sets, it's a little bit more difficult to use KNN. It needs to calculate the distance for all the different neighbors, so that can take a lot more. It has more costs on the computation. So some neural networks are a bit better for the larger data sets. And this is a chart that compares the model accuracy by digit. So you can see that for digits that are more similar, like 3 and 9, or I mean 4 and 9, they're a little bit lower than like 1, 0, 6, 7 and 4 are pretty similar too. Yeah, we thought this chart was pretty cool. And this has a breakdown of the performance by digit, and the by KNN and neural network and the difference. And this just has the different batch size speed. So a smaller batch size has a quicker training time per image, and the larger, or for the KNN. And as the batch size gets larger, the neural network has a better prediction time. So yeah, I don't know if you want to add anything there, Tony, or yeah.
No, I think you covered it all. My favorite part is that chart, like of the whole
Yeah.
piece, looking at those numbers, like the 9, 96 versus 92. But there's also the number 1, which is better with the KNN, just in what we did. So yeah, there was
Yeah.
one more thing I just want to show. I'll share my screen really quick. Um, so just as we're looking at here's our project. If you want to see our source code, if you click on Quarto presentation, so we use Quarto, which is like our our markdown, and we publish it with the command that I must have took it out. But basically, there it is, and then here's all the Python for it. We try to keep it all in one big giant data set. Commented out these methods because we didn't use them. I thought that I took them out. Yeah, but that's everything. So it's been a lot of fun. I love taking this. I love taking this class. I really, really super love this problem, and I think it should be one of the things that we all start with when we jump into the 622 program. What do you think, Kristen?
Yeah, I think it was pretty easy to implement, and it was really interesting learning more about the history of the problem and how it's so much easier to do this problem now than it was in the past. Um, yeah, like when I first was reading about it, I was like, how are we going to be able to implement this? But it wasn't that as difficult as we expected. So yeah,
I was a little scared too, but
yeah,
I remember texting you. I was like, well, let's do it. You're like, oh, okay, you sure?
yeah,
All right. Anyway, thanks everybody.
yeah.
Bye.
Thank you. Bye.